Hello and welcome everybody. So we just spent a little bit of time on differential equations, and now we're kind of heading back away from differential equations. In some ways, there was a culmination into differential equations, but you didn't see too much of the physics and the quantum mechanics that I think is kind of underlying this entire course when we analyze those differential equations. So now, in some sense, we've finished all of the quote unquote particularly new material, but now we're going to kind of hone in on the quantum mechanics and kind of where all of the physics, which all of our older material can apply to, exists. We're not really going super deep into quantum mechanics, but what we're doing is we're just going to learn a little bit more of the language that people use when they refer to quantum mechanics. And certainly if you take any of these physics or physical chemistry courses and learn about it, they'll be using these languages. So that's what's going to be kind of finishing up the semester. And with that said, the title of this section is Unitary and Orthogonal Maps, which maps include matrices and operators, since really we're talking about linear maps here. So matrices in finite dimensions and operators in infinite dimensions. And primarily, what are these maps going to be? Well, matrices, I think you've all been very comfortable with those for a while now. Operators, you could probably think about as infinite dimensional matrices in some senses, but you can also think, your ddx is a case, but when we're talking about unitary orthogonal, let's put an I in front of it, or d squared, dx squared. There's all sorts of these things with operators, matrices. Everybody knows what matrices are, so we've been working with those for quite some time. What do these adjectives mean, unitary and orthogonal? We kind of have to push ourselves into a realm of what physicists and also mathematicians like to call symmetries. So there's this word symmetries that gets thrown around. That does have a fairly precise definition in math and physics circles. We can interpret the word symmetries as meaning a transformation or process which leaves a quantity unchanged. And you should think about this word quantity underneath some quotations. It can be broader than quantity. But let's just take an example. When we say that our bodies have mirror symmetry, what we really mean is we have a symmetric about a flip over our vertical center, or vertical axis, maybe I'll say. Right, here's my body. I've been working out, can you tell? So there's my body. We grab the vertical axis and we decide to do a flip. Not an easy way to describe a flip, but if we just grab a flip of my body over the vertical axis, what do we end up with? Exactly what we started with. So in some sense, the quantity is my body itself. Right? So the quantity is maybe the shape of my body. Certainly, if I swapped backwards in some mirror symmetry myself, I'm right-handed right now. I would all of a sudden be left-handed. So there are definitely some psychological and physical factors that would slightly change, but you understand the overall notion of this shape of the body remains unchanged. I think a lot of people wouldn't be able to tell that I've been flipped until I decide to write with my left hand. And so you leave this quantity unchanged under a flip. We could also say, let's say a water bottle has rotational symmetry, and rotational of any amount is pretty cool symmetry. And it's only true though around its vertical axis, right? Because if I grab a water bottle, I'm going to do my best to draw a water bottle here. Maybe it looks like this. Maybe it's got a little label on it. And then usually they have like weird ridges on the sides. I'm sure that's to give the plastic some structural integrity. And then it's got its little cap, and usually the cap has a little thing next to it. Okay, it's a nice water bottle. And we grab its vertical axis, and we rotate. Let's rotate by theta degrees. And that water bottle, I'm not even going to try to draw it again. That water bottle looks the exact same. It looks exactly like it started with, even under a rotation. And so we say that one has a symmetry where the quantity is again a shape. But we we do often use the word symmetries for, non-shape objects. So actually the physicists would go so far as to say that laws like conservation of momentum is a symmetry. In some sense, we move forward in time, right? So after moving forward in time, moving forward in time is, of course, a transformation. We are transforming as we speak. Moving forward in time, this is a transformation. The quantity of momentum is unchanged. So these are all versions of symmetries, and in fact unitary and orthogonal maps are those which describe, they're linear maps which describe geometric symmetries. They are linear maps which, when applied to vector spaces, preserve two things. They preserve angles and they preserve size. So these are the symmetries. They preserve exactly two things about vector spaces, angles and size. And this application, right, so when applied to a vector space, they perform some sort of transformation. But that transformation preserves angles and size. What it doesn't preserve is orientation. And maybe I'll mention this. It's really kind of two things. So there's orientation, and secondarily, chirality is technically the word we use. This is handedness. So when I originally said that if I took a mirror, if I mirror flipped myself up top here, starting out as a right hand and then ending up as a left hand, that's totally fine subject to unitary and orthogonal maps. They are more than happy to swap my left hand for my right hand. Because even if I did that, my hands stay the same size and they share the same angles. So we're not worried about, we're not going to preserve chirality or my handedness, and we're not going to preserve orientation. So orientation is fairly straightforward. That would be, balance me on my head instead of my legs. So you can spin me in whatever direction you want. You can also possibly flip me around through a mirror. So how do I identify these? And in particular, I'm going to give these, there's a reason why we have two of them. Unitary just deals with complex vector spaces, and orthogonal deals with real vector spaces. So it just depends on if we decide we want to sit inside of a complex space or a real space. Let's talk about identifying these. So how to identify unitary and orthogonal maps. Well, they're linear maps, so they both have matrices, right? So the first thing we're going to do is make sure that we have a matrix representation. So we're going to construct the matrix representation. This, of course, only applies to finite dimension. I'll show you how to play games without matrix representations in infinite dimensions. Secondarily, we have something called a transpose. So we're going to perform a transpose on the matrix. And I'll show you what that looks like here. A transpose has some notation. So it's denoted by M, and then we just put a capital T and a superscript of the M, T for transpose, and defined by, if M has its superscript subscript notation, ij going from 1 to some dimension n, then M transpose is defined by mji. So you're actually swapping rows for columns. So what happened here is I've swapped the rows and columns. Now nobody likes it when I define transpose like this, so more easily you can think about A, B, C, D. Transpose equals, you take this downright diagonal line and you reflect over the diagonal. And that's all people ever need. to figure out what to do. The diagonals always stay the same. I've reflected, so I get B and C now. That's the transpose for maybe a 2x2 matrix. Let's do it for a 3x3. If I take the transpose, I'm going to look at my diagonal. I'm going to reflect over the diagonal. And so what happens here, that's including the C and the G as well. So what we get is we get A, B and D swapped places, D, C and G swapped places, G, and then B and D swapped places, so B, E stayed the same because it's in the middle, F and H swapped places, H, C and G swapped places, F and H swapped places, and I is on the diagonal, so it stayed the same. Go ahead and make it a little prettier here. So we're just going to reflect over the diagonal. You can basically see we now are just doing A, B, C, D, E, F, G, H, I. So that's all that happens when you perform a transpose. And a complex conjugate, if there are complex entries. So a complex conjugate, if there are complex entries, I think everybody knows what that's going to be, denoted by a bar. This is going to be M, I, J, bar. I, J go from 1 to N. This is going to be M, I, J, bar. You just look at the entries. I, J goes from 1 to N. So together, we denote, we have a shorthand for them together. M, complex conjugate, and transpose. The order doesn't matter. You could do M, transpose, complex conjugate. This is often denoted with a dagger. So this mathematical symbol is called the dagger. Kind of looks like a dagger. I kind of get it. Dagger. And this is known as the adjoint or Hermitian adjoint. Especially in physics circles, you may hear Hermitian adjoint a lot more often. But in general, I'll just call it the adjoint, putting a dagger up top. So we're going to calculate either the transpose or the adjoint. And of course, if the matrix is real, then the complex conjugate didn't do anything anyway, in which case the adjoint is the transpose. So you can really think about always doing the adjoint. And then step 3, we're going to compute the matrix against its adjoint. And you're going to test if that's equal to the identity. And maybe I'll just say you compute it if it is the identity matrix, then M is unitary if complex, and it's orthogonal if real. That's all you have to do. You just compute the matrix multiplication of the matrix against its adjoint, and if you get the identity matrix out, you're either unitary or orthogonal. So not too terribly hard. Performing the transpose, you just have to get a little bit used to. And then you just go ahead and perform these matrix calculations. We'll cover the infinite dimensional case later, but let's just look at some examples. So the first example is the matrix 1 divided by the square root of 2 on 1, 1, negative 1, 1, unitary or orthogonal. Well, the first thing we can do is we can say, note, this is real. And so forget about the word unitary. We're only going to test orthogonal. They mean the same thing. I'm honestly frustrated that we give them different names because they do mean the same thing, just reduced to the real vector space case. Don't get mad at me if you know why we give them different names. I also know why we give them different names. It's so that we can classify them, but in general, it confuses people more than it helps them when they're learning because they're really the same sort of thing. All we need to do is we need to compute, right, a matrix representation. Boom, it's already done. Now, suppose I was given the linear map. Okay, suppose instead we started with L of x1, x2 sends me to 1 over root 2 x1 minus 1 over root 2 x2, and then 1 over root 2 x1 plus 1 over root 2 x2. Okay, fine. In that situation, sure, you would have had to had to do this step 1, but we didn't start there, so we already have a matrix representation. Step 2, we need to perform the transpose and the conjugate. But it's real, so no need. There's no need for a conjugate when we're real. Conjugate of every real number is a real number, the same real number. So we'll take a transpose. 1 over root 2, 1, negative 1, 1, 1. And let's go ahead and transpose this, which means I'm looking at the downright diagonal, and I'm going to flip everything over the downright diagonal. That's going to leave me with 1 over root 2. Flip everything, that becomes a 1. This becomes a negative 1. Step 3, compute m against m dagger, which in this case is m transpose because it's real. So we're just doing 1 over root 2. M is up top here, right? So we'll do 1, negative 1, 1, 1, multiplied by 1 over root 2. The transpose is over here on the right. And then we perform a matrix multiplication. So we're going to do rows against columns. 1 over root 2s are going to square each other, right? We get 1/2. The top row against the left column gives me 1 plus negative 1 squared, also known as 2. And then the top row against the right column gives me 1 minus 1, also known as 0. The bottom row against the left column gives me 1 minus 1, also known as 0. And the right row against the bottom, or the bottom row against the right column gives me 1 plus 1, also known as 2. This gives me, once I pass 2, 1/2 to the inside, 1, 0, 0, 1. Does that look familiar? That is, in fact, the identity matrix, which is exactly what we were looking for. So yes, this matrix is orthogonal. Let's do one more example looking at unitary. Is the matrix 1 over root 3, 1, 1, 1, 1, e to the I, 2 pi over 3, e to the minus I, 2 pi over 3, and then 1, e to the minus I, 2 pi over 3, e to the I, 2 pi over 3, unitary or orthogonal. And then this may look kind of weird. We've got all these complex exponentials sitting around. It turns out that complex exponentials are really just like rotations in the complex plane. So really what's happening is we're considering 3 vectors, 1, 1, 1, that's been normalized, 1, and then a bit of a complex rotation in the conjugate direction, and then vice versa, and they've all been normalized. So this feels strongly that maybe it's probably unitary, but we should go ahead and find out. First thing we can note is that since this has complex entries, we basically guarantee ourselves to ask the question about unitary. We don't have to ask about orthogonal, kind of like before. And we're going to do the exact same thing as prior. Okay, we're not going to consider that. Maybe we started with a linear map here. So case number 1, getting it into a matrix, is once again already done. What we need to do in step 2 is compute the transpose, 1 over root 3, times 1, 1, 1, 1, e to the I, 2 pi over 3, e to the minus I, 2 pi over 3, 1, e to the minus I, 2 pi over 3, and e to the I, 2 pi over 3. We're going to go ahead and transpose this, which means we look along the diagonal, and then we're going to swap all of these terms that are not on the diagonal, rotate around the diagonal. And in this case, we see those are actually all the same. They swap with their partners, and their partners are the same, so we're pretty good at just rewriting it. But then we do also need a complex conjugate, and complex conjugate. So now we're going to grab what we've just computed and take its conjugate. That's going to be 1 over root 3, 1, 1, 1, 1, e to the I, 2 pi over 3, e to the minus I, 2 pi over 3, 1, e to the I, minus I, 2 pi over 3, and e to the I, 2 pi over 3. And go ahead and apply a complex conjugate to this entire piece. That's really only going to apply to these 4 cases, and we're going to replace I with minus I. That's what the complex conjugate tells me to do. So that's going to bring me to 1 over root 3 Basically what it's doing here is it's now going to give me a minus I 2 pi over 3 in the first case, and a plus I 2 pi over 3 in the second case, vice versa, e to the positive I 2 pi over 3, e to the negative I 2 pi over 3. This is going to be M dagger. This is the Hermitian conjugate, or the Hermitian adjoint. Step 3, I need to check M multiplying its Hermitian adjoint. So I'm going to multiply its adjoint. That's going to be 1 over root 3. M is just 1, 1, 1. 1 e to the I 2 pi over 3. E to the minus I 2 pi over 3. 1 e to the minus I 2 pi over 3. E to the I 2 pi over 3. There's another 1/3, or 1 over root 3 coming along. Then I have 1, 1, 1. This is my adjoint, right? 1, 1, 1. 1 e to the minus I 2 pi over 3. E to the I 2 pi over 3. 1 e to the I 2 pi over 3. E to the minus I 2 pi over 3. Then I compute, as always, all rows on the left against all columns on the right. And the 1 over root 3's are coming along, 2 of them, so I have 1/3 total. If I look at my top row against my left column, it looks like I have 1 plus 1 plus 1, so I have a 3. If I look at the top row against the middle column, I have 1, and then I'm adding e to the negative I 2 pi over 3 to e to the positive I 2 pi over 3. Now it's not clear why this should be the case. What's happening here is I'm summing 3 vectors, or even the complex numbers. Let's compute all of them with Euler's formula. So I have 1, and then Euler's formula, so I have a cosine of negative 2 pi over 3 plus I sine of negative 2 pi over 3. That's the first case. And the second case is going to give me cosine of 2 pi over 3 plus I sine of 2 pi over 3. Let's go ahead and think about our lovely unit circle. Where's 2 pi over 3? That's over here. The x value there is negative 1/2. The y value is root 3 over 2. So there's cosine and sine for you. Negative 2 pi over 3 is over here. The x value is negative 1/2. The y value is negative root 3 over 2. So what we end up with here is 1, and then the cosine of the negative 2 pi over 3 is negative 1/2. Then I have plus I. The sine, negative 2 pi over 3 is negative root 3 over 2. And then I have plus cosine 2 pi over 3 is negative 1/2. Plus I sine 2 pi over 3 is positive root 3 over 2. And of course, it's everything that you probably expected from the beginning. 1 minus 1/2 minus 1/2, there's a 0. From the 1, there's also a negative root 3 over 2 and a positive root 3 over 2. So I'm actually getting 0 out of this entire term. So I'll keep that in mind when I continue now, because if I look at the top row against the far right column, that's going to give me 1 plus e to the I 2 pi over 3 plus e to the minus I 2 pi over 3. And that's what we just calculated as 0. Then if I look at the middle row on the left column, I have 1 plus e to the I 2 pi over 3 plus e to the minus I 2 pi over 3. Big surprise, that's 0. If I look at the middle row against the middle column, what's happening in the middle row, middle column, I have a 1. I then have e to the positive I 2 pi over 3 and e to the negative I 2 pi over 3. So those exponents are adding together, and I have a positive and negative term. I have e to the 0 power. E to the 0 power is 1. And then the last term, I also have a positive exponent and a negative exponent. Multiplying, I get another 1. And my middle term here becomes 3. If I look at the middle right, the middle row against the right column, I have 1 plus e to the I 4 pi over 3. And then I have plus e to the minus I 4 pi over 3. I'm not going to waste my breath. Same reason as before. These are also canceling to 0. You would just have to go through a brand new round of Euler's formula to find that out. We can look at the bottom row against the far left column. 1 plus e to the negative I 2 pi over 3 plus e to the I 2 pi over 3. As always, that's canceling and giving me 0. If I look at the bottom row against the middle column, I'm going to have the cases where I have a total of e to the minus I 4 pi over 3 and e to the positive I 4 pi over 3. But as before, that's also going to cancel to 0. And my bottom right term, I'm again going to have a 1 times a 1. I'm going to have a positive exponent times a negative exponent and a positive exponent times a negative exponent. It's giving me 3 copies of 1, also known as 3. This is going to give me 1/3 times the matrix 3, 0, 0, 0, 3, 0, 0, 0, 3. If I pull the 1/3 all the way through, I get 1, 0, 0, 0, 1, 0, 0, 0, 1. And so we see we have exactly the identity matrix, even though it was a heck of a time to get there. Once we have the identity matrix, we can verify that our original M was unitary. So if I go up to the very top, is the matrix unitary? Yes. Okay, so those are the 2 examples I'm going to go through today. I'm going to go through another few properties that are equivalent definitions of unitary and orthogonal. Because I gave you this nice process of checking if things are unitary, right? How to identify unitary and orthogonal. That doesn't really define them. You could argue that this definition defines them, preserving angles and size, but in reality, the following 2 definitions are probably what you should look for. So let's go with the true definitions. A matrix O, and a lot of times they'll write it as a script O, so I'll go along with that. Instead of writing big O, I'll write script O. So a matrix script O is orthogonal if it is real, okay, so real entries, and the columns form an orthonormal basis. That's why we call them orthogonal in the first place. That's really where the name came from. So if it's real and if the columns form an orthonormal basis. Equivalently, O is orthogonal if O times its transpose is the identity, which is equivalently O transpose times O. And even more equivalently, if O transpose equals O inverse, right? These are all kind of saying the same thing. And we can do the same thing when it comes to unitary. A matrix. I'm not really going to go for the script U. Maybe I'll make it a little bit scripty by putting a little bit of a hole in the stem there. A matrix U is unitary if it is complex entries, and the columns form an orthonormal basis. Equivalently, U is unitary if U dot U dagger is the identity, which is the same as U dagger dot U, or even more equivalently, if U dagger equals U inverse. Now, let's comment on the etymology. Remark the etymology of unitary, because orthogonal comes straight from orthonormal, right? On unitary, we've got something else. There's the unit word in there. Is that if I look at the norm of the unitary matrix acting on a vector, that will give me the norm of the vector. So in some sense, it pulls out of a norm as a unit. Now this doesn't necessarily define unitary maps. This is a property of unitary maps. So that's where the etymology comes from. We really should look above for the definition of unitary maps, even though the etymology is that it's going to be true. I'll make a quick comment on the definition in infinite dimensional settings. Okay, which means we may not have a matrix. So we lose transposes or adjoints, at least in the way I've defined them earlier. We call a map U unitary if the inner product of u against a function and then another function for an infinite dimensions, these are basically the function spaces, right, is equal to f against u on g for every possible f and g in whatever vector space we happen to be in. So in some sense, this process of moving u over, this is somewhat like, oh, and this should be an inverse, u inverse. If u on fg is equal to f on u inverse of g, this is somewhat like the transpose. When I test it on the other side, or even the conjugate transpose, when I test it on the other side of the inner product, that's the idea of doing a conjugate transpose. And in fact, we do call it an adjoint, but it's just that you can only work with inner products. You don't really get to work with flipping matrices over the downright diagonal. So we're going to see this notion play a little bit more of a role in later videos in infinite dimensions. Anyway, I'll stop there for the day. It's pretty cool. These are the matrices which define all of the transformations which preserve our angles and size physically. Okay, so if we're talking about, even in 3 dimensions, every rotation in 3 dimensions, because it preserves angles and size, you know that the matrix corresponds to an orthogonal operator. Anyway, I'll leave it at that. I'll see you in the next video. Bye.